Good morning. Today we can take topic subgroup part 1, that is subgroup and their properties. I'm Mr. S.R. Gaikwad, Assistant Professor in Department of Mathematics, Arts, Commerce and Science College, Alva. Please subscribe my YouTube channel, Mr. S.R. Gaikwad. First, definition of subgroup. A non-empty subset H of a group G, star is said to be subgroup of G if H itself a group with respect to same binary operation star. Here H is a non-empty subset of group G. G is a group, it means G satisfies all four conditions of the group. And H is a non-empty subset of G. Then H is called subgroup of G. It means H is also satisfy the same condition of the group with respect to same binary operation star. And at that time, H is called subgroup of G. Proper and improper subgroup. Let G, star be a group with identity element E. Then singleton E and G itself are subgroup of G. That is singleton is subgroup of G. G is also subgroup of G. Then these subgroups of G are called improper or trivial subgroup of G. It means singleton E and G are called improper subgroup or trivial subgroup of G. Any other subgroup H of a group G is called a proper or non-trivial subgroup of G. For example, 2z, plus is a subgroup of z, plus z nothing but set of integer, 2z nothing but set of all even integers. Z, plus is subgroup of q, plus q nothing but set of rational number. Q, plus is subgroup of r, plus r nothing but set of real number. Also, 3z, plus is subgroup of z, plus. In general, nz, plus for all n belongs to set of natural number is a subgroup of z, plus. Criteria for a subgroup. Theorem first. A non-empty subset H of a group G, star is subgroup of G if and only A star B inverse belongs to H for all A, B belongs to H. Proof. Let G, star be a group and H is non-empty subset of G. Part first. Suppose H is subgroup of G. H is subgroup of G. It means H, star itself a group, that is H satisfy all conditions of groups. We have to prove A star B inverse belongs to H for all A, B belongs to H. We can take two elements. Let A, B be any two element of H. Now, element B belongs to H and B is itself a group. It means inverse exists. Therefore, B belongs to H implies B inverse belongs to H. And therefore, A belongs to H, B inverse belongs to H. By closure property, A star B inverse belongs to H. And therefore, A star B inverse belongs to H for all A, B belongs to H. That satisfies the condition. Part second. That H is non-empty subset of G for which given condition A, B belongs to H implies A star B inverse belongs to H is false. Using this condition, we have to prove H is subgroup of G. Now, claim H, star is group. Now, H is non-empty subset of G. It is given. Therefore, at least one element say A belongs to H. It means H contains at least one element. We can take that element as A because H is non-empty. Now, this element A belongs to H, and therefore, first condition we have checked existence of identity. By given condition, A belongs to H, it means we can take A, A belongs to H. It implies that first element star inverse of second element also belongs to H. It means A star A inverse belongs to H. But value of A star A inverse nothing but identity element, and therefore E belongs to H. It means identity element exists in H. Second, existence of inverse in H. Let A belongs to H, identity element is also belongs to H, and therefore by given condition E, A belongs to H implies E star A inverse belongs to H. But value of E star A inverse nothing but A inverse belongs to H. It means A inverse of every element exists in H and therefore inverse exists. Then closure property. We can take A comma B two elements of H. Here inverse exists, A belongs to H implies A inverse belongs to H. It means B belongs to H implies B inverse also belongs to H. And therefore A comma B inverse both elements are belongs to H. Then by given condition, first element star inverse of second element is also belongs to H. It means A star B inverse bracket inverse belongs to H. But B inverse bracket inverse is same as B. It means A star B belongs to H. Therefore, closure property is satisfied. It means star is closed with respect to binary operation. Associative law. Let A, comma B, comma C belongs to H. Therefore, A, comma B, comma C belongs to H implies A, comma B, comma C belongs to G, and G is a group. G is a group. It means associative law hold in G, and therefore A star then in bracket B star C equal to A star B bracket complete star C. This condition is hold in G, and therefore H satisfy four. H is also satisfy the associative law. It means H satisfy all four conditions of group with respect to binary operation star, and therefore H comma star is a group. But H is subset of G, and therefore H is a subgroup of G. Remark. The condition A comma B belongs to H implies A star B inverse belongs to H is equivalent to two conditions. A comma B belongs to H implies A star B belongs to H, and A belongs to H implies A inverse belongs to H. It means H is subgroup of G. Then A comma B belongs to H implies A star B inverse belongs to H, which is equivalent to A comma B belongs to H implies A star B belongs to H, and A belongs to H implies A inverse belongs to H. Theorem second. A non-empty subset H of finite group G comma star is subgroup of G if and only if A comma B belongs to H implies A star B belongs to H. Now, let G comma star be a finite group and H is non-empty subset of G. Here given that G is finite group and H is non-empty subset of G. Part first. Suppose H is subgroup of G. Therefore, H comma star is a group. Let we can take A comma B any two element of H. A and B are any two element of H, and H satisfy all conditions of group, and therefore by closure property A comma B belongs to H implies A star B belongs to H also. It means if H is finite group, then A comma B belongs to H implies A star belongs to H. This condition is satisfied by using the closure property. Second part. Let H is non-empty subset of finite group G, for which A comma B belongs to H implies A star B belongs to H. This condition is hold. Then we have to prove H is subgroup of G. Claim H is subgroup of G. Since G is finite, therefore order of every element of G is finite. Let A belongs to H implies A belongs to G, so order of A is finite. Let we can take order of A equal to, suppose order of A equal to n. Order of A equal to n, it means A raised to n equal to identity element where n is least positive integer. Now, given condition is A comma B belongs to H implies A star B belongs to H. In that given condition, we can replace B by A. It means A comma A belongs to H implies A star A, which is same as A square is also belongs to H. Now, A comma A square belongs to H implies A star A square, which is same as A cube, which is also belongs to H. Similarly, A raised to 4 is belongs to H, and so on. A raised to n is also belongs to H. But A raised to n nothing but identity element. It means identity element is belongs to H. It means identity element exists. Second. Also in above process, a raised to n belongs to h. Here a raised to 4 belongs to h, it means a raised to 3 is also belongs to h. Here a raised to n belongs to h, it means a raised to n minus 1 is also belongs to h. But a raised to n minus 1 is same as a raised to n star a inverse belongs to h. But the value of a raised to n is identity element, and therefore E star A inverse belongs to H. It means A inverse belongs to H. It means inverse exists in H. Third, from given condition A comma B belongs to H implies A star B belongs to H. It means clearly closure property is satisfied. As the composition in G associated as composition in G is associative, and the elements of H are also element of G, and therefore associative law is also held in H, and therefore H satisfy all conditions of group, and therefore H is subgroup of G. Properties of subgroup. The identity element of a subgroup is same as that of the group. Second, inverse of any element of subgroup is same as the inverse of the same element that of the group. Third, order of any element of subgroup is same as the order of that element of a group. Next, intersection of subgroup theorem. If H1 and H2 are two subgroup of group G, then H1 intersection H2 is also subgroup of G. Proof that H1 and H2 are two subgroup of a group G. Clearly, H1 and H2 are two subgroup. It means H1 and H2 also contain the identity element because they satisfy all conditions of the group. It means identity element exists, and therefore E belongs to H1, E belongs to H2. It implies that E belongs to H1 intersection H2, and therefore clearly H1 intersection H2 is not equal to 1. Let A comma B belongs to H1 intersection H2. We have to prove H1 intersection H2 is a subgroup. A comma B belongs to H1 intersection H2. It implies that A comma B belongs to H1 and A comma B belongs to H2. And therefore, H1 is subgroup of G. And by criteria, A comma B belongs to H1 implies A into B inverse belongs to H1. Also, H2 is subgroup of G. And A comma B belongs to H2 implies A into B inverse belongs to H2. And therefore, A into B inverse belongs to H1. A into B inverse belongs to H2. It implies that A into B inverse belongs to H1 intersection H2. And therefore, A comma B belongs to H1 intersection H2. It implies that A into B inverse belongs to H1 intersection H2. It means H1 intersection H2 is a subgroup. Remark. The arbitrary intersection of a subgroup of a group G is again a subgroup. We can take any number of finite number of subgroup. Their intersection is also subgroup. That is, if H1, H2, the H3, that Hn are subgroups of G, then their intersection H1 intersection H2 intersection S3 intersection dash dash intersection Hn is again a subgroup. In general, union of two subgroups of a group G may or may not be subgroup. For example, Z plus be a group with respect to binary operation addition. 2Z plus and 3Z plus are subgroups of Z plus. 2Z plus is nothing but set of all integers multiple of 2. 3Z nothing but set of all integers multiple of 3. 2 belongs to 2Z, 3 belongs to 3Z. It means 2, 3 belongs to 2Z union 3Z. But 2 plus 3 equal to 5 does not belongs to 2Z union 3Z. Therefore, 2Z union 3Z is not a subgroup. It means union of two subgroup need not be a subgroup. Here 2Z and 3Z are subgroup, but 2Z union 3Z is not subgroup with respect to binary operation of addition. The union of two subgroups of a group G is a subgroup of G if and only one of them is contained in other. That is, if H, K are subgroup of G, then H union K is subgroup of G if and only H is subset of K or K is subset of H. Proof that H, K are subgroup of G. Part first. Suppose H is subset of K or K is subset of H. Now, case first, if K is subset, H is subset of K, implies H union K is same as K, which is, and K is subgroup, it means H union K is a subgroup. So we can suppose that H is subset of K or K is subset of H. We have to prove that H union K is subgroup. But we know that if H is subset of K, at that time H union K is same as K. But K is subgroup, it means H union K is subgroup. Second case, if K is subset of H, implies H union K is same as K, but K is subgroup, and therefore H union K is subgroup. And therefore, in both cases, H union K is subgroup G. Second part, assume that H, K are subgroup of G such that H union K is subgroup of G. Then we have to prove H is subset of K or K is subset of H. Claim that either H is subset of K or K is subset of H. If possible, H is not subset of K and K is not subset of H. Now, H is not subset of K. It implies that there exists at least one element A which is belongs to H but A is not in K. And K is not subset of H. It means there exists at least one element B belongs to K but B is not in K. Now, A belongs to H, B belongs to K. Implies A, B belongs to H union K. And H union K is a subgroup. And their first element into inverse of second elements also belongs to H union K. A into B inverse belongs to H union K. It means A into B inverse belongs to H or belongs to K or belongs to both H and K. First case, if A into B inverse belongs to H, A into B inverse belongs to H, we imply that A, B inverse bracket inverse is also belongs to H because H is subgroup inverse exists. But A, B inverse bracket inverse is same as B into A inverse by reverse law of inverse. And therefore B into A inverse belongs to H. A is also belongs to H. And therefore by closure property, B into A inverse into A belongs to H. But B, A inverse into A is nothing but identity element. It implies that B belongs to H. But B is not in H, which is contradiction. Therefore, if A into B inverse belongs to H, implies B belongs to H, which is contradiction. If A into B inverse belongs to K, and B also belongs to K, and therefore by closure property, A into B inverse into B belongs to K. But B inverse into B nothing but identity element. It means A belongs to K, but A is not in K. And therefore, A into B inverse belongs to K implies A belongs to K, which is contradiction. And therefore, our assumption H is subset of K or H is not subset of K or K is not subset of H must be wrong. If you consider here, if possible, H is subset of H is not subset of K and K is not subset of H, this assumption is wrong. That is, H is subset of K or K is subset of H. It means if H union K is subgroup of G, and at that time either H is subset of K or K is subset of H. So in this topic here, we can define subgroup. A non-empty subset H of a group G, star is subgroup of G if H itself a group with respect to same binary operation star. This definition of subgroup. In this topic, we can summarize this definition of subgroup. This H is non-empty subset, and if itself a group with respect to same binary operation star, then at that time H is called as a subgroup of G. Then we have to the criteria for subgroup. A non-empty subset H of a group G, star is subgroup of G if and only if A star B inverse belongs to H for all A, B belongs to H. Also, a non-empty subset H of finite group G, star. Here G is finite group of a subgroup. A non-empty subset H of finite group G, star is subgroup of G if and only if A, B belongs to H implies A star B belongs to H. Here G is not found. Here G is only G, star is a group. At that time, A, B belongs to H implies A star B inverse belongs to H, then H is subgroup. If G is finite group, then H is subgroup of G. If A, B belongs to H implies A star B belongs to H. Next, H1, if H1 and H2 are two subgroup of G, then H1 intersection H2 is also subgroup of G. It means intersection of any two subgroup is again a subgroup. If H, K are subgroup of G, then H union K is subgroup of G if and only if H is subset of K or K is subset of H. Union of two subgroup of a group G may or may not be subgroup of G. It means union of two subgroup need not be a subgroup. Thank you. Please like and share this video and subscribe my YouTube channel, Mr. SR Guy.